All right, everybody. So for our assignment 7 for CS302, we're going to once again be using a hash map to solve a problem. But for this assignment, we're going to be creating our own custom hash map. So what this program is going to really be about is we're going to really create some type of a vote counter, tallying of votes for some election. So the assignment, the way it's going to go, so I'll go over a formal like input-output description towards the end, but for right now what we're going to do is we're going to have a set of candidates, each with a party affiliation or independent, and then we're going to have then a set of ballots or votes on a candidate. We want to tally those up and output the party of the candidate that won the election. And to do this, we're going to use a hash map structure to implement this algorithm to make this faster than a standard brute force approach. So let's go ahead and go over the actual class structure for this assignment. Alright, so this is going to be our class hash map. So we're going to have a templated type with two types, T1 and T2, where T1 will be our search key type and T2 will be our value type. So looking at our structure, we have our struct hash pair. So that is going to be each element in our hash map. So we're going to go over the iterator pair later. Let's first focus on hash pair. So this hash map is going to really use this separate chaining mechanism to maintain all of our entries in our hash table. So you're going to have an array of linked lists. So a hash pair is going to really be a node. We have our T1 search key, our T2 value, and a pointer that points to another entry in our linked list for whichever index we're in our hash table. Now, luckily, this is going to be a simpler version, and we're going to have a hybrid version of this with linear probing. So, in other words, what's going to happen, if you remember our notes on separate chaining for hashing, we're going to have an array of linked lists, and for this implementation, each linked list can have at most 2 nodes. So that's how we implement this hybrid method. So if we have 2 nodes already stored in one of the linked lists, and in both nodes we don't find our search value, then we have to linear probe to the next element in our table. So we'll go over details of that in a second, but that's sort of the high-level view of what's going to happen here. So each entry will be a node with a key, value, and a link to the next node in our linked list. We're going to avoid our iterator for right now. Let's go over our constructor and destructors. Let's go over constructor first. So we see here in our private members we have items, size, and then this hash pair star table. So this table is going to be our hash table. Same way I implemented this, same way as we did in class when we talked about this array of linked lists, separate chaining methods. So this is going to be our hash table. So our constructor is basically going to set our items counter to be 0. The size is going to be 5, I believe, for this assignment. Let me just double check that here. If you have the constructor content written over here. Yes, so it sets the size to 5. So you can see that right here in the description. So that is the correct value to set the size to. Items will be 0. And we're going to allocate an actual array of linked lists. We're going to say new hash pair star and of course size, and then set every element to be null. Now head, this, I didn't go over iterator pair really just yet, but the head is going to basically be a linked list of all of our entries. So remember with when we use an unordered map, we have that iterator that iterates through all of the elements that are currently stored in our hash map. So this linked list is going to just store all of the key value pairs we have in our hash map if you want to, of course, cycle through them. But of course, if you want to look up an entry, it's going to be in this table right there. So our constructor just does that. The destructor is going to have to basically deallocate this structure, this table. So you have to go through each element of this table array and deallocate each node in each linked list from table 0 to table 1 up to table size -1. And then of course deallocate this array of pointers. And of course the destructor has to deallocate this linked list of this head, this linked list of actual key value pairs stored. I didn't go over iterator pair just yet, but really do a simple standard linked list deletion. That's all there is to that. So now I'm going to go over the details of the bracket operator, and I think I probably will go over the iterator content next before, so that way I can actually really explain the bracket operator in much more detail. Okay, so one thing I forgot to talk about first was the hash function int age. This hash function is pretty simple. You pass in a string, so we're going to have this hash function be specific for string as your key type. So this function takes in a string, it's going to add up all the ASCII characters of that string, mod it by size, and return that amount. Now if you want to have different type of keys, different type of search keys you want to use for this hash map type, then you can feel free to overload more than one hash or age function. And of course, the resize function, I'll kind of walk you through a little bit of this. I did go over resizing in class, but I'll go over just maybe some hints towards the end of how you want to work on a resize function. So let's go ahead and just talk about the iterator and iterator pair. So if you notice this, the hash pair and the iterator pair are they're similar but different. Notice that we have T1 key, T1 star key, T2 value, T2 star value. Now, the way this works is hash pair is going to be a node in your hash table that contains different entries in your table. The iterator pair is going to store all of the keys and values in a separate linked list, so if in main you want to cycle through them, then you would be able to. Now, the deal here is T1 star key is not going to contain an actual key. It's going to contain a pointer that points to a node, points to a key field within a node in your hash table. I have a picture for this so you can see this in a second. The same thing for the T2. It's not going to contain a value, it contains an address or pointer to a value of an existing entry in your hash table. The purpose of it is we're doing a shallow copy in a way of the key and value of an element in a table with what's in this iterator pair. So the whole idea is that as we search, if we do in fact update the values, or maybe even a key, so I guess the keys will remain fixed, but the values for sure are going to be updated. We don't want to have to just copy it. If you want to be able to just sort of, if you update the value in the node in the hash table, the value updates automatically as well. So I guess the key didn't have to be a pointer, but I kind of want to keep them consistent so it wouldn't really throw us off too much. So that's going to be what the iterator pair contains, but I'll go ahead and of course I'll have a picture drawn up where you can kind of see this a bit better. So let's go over the iterator class for a second. So once again, we have the friend class HashMap, and the whole idea is that this is going to allow the HashMap class to access private members of the iterator if needed. So iterator, we have this constructor, this constructor, and we have also the this element pointer. So it points to a node in that linked list in this linked list rooted by the pointer head. So we have this pointer element. So basically this plus plus operator is going to move element over to next element in that linked list. So it's going to literally just be element equals element arrow link return star this. Equals equals not equal. Similar to our previous assignments, all we're going to do is compare two iterators. So we compare their element pointers. So this element with this RHS dot element, and same thing for not equal, we compare them. So if equal to each other, if they point to the same node, return true, else false, and if not equal, it's the opposite. It returns true if this arrow element does not equal RHS dot element, and so forth. And then T1 first, T2 second are two functions which return the first, that key field. It returns the key field, and T2 second, it returns that value field. Just like very similar to the unordered map, except not going to be arrow first, it'll be dot first, left and right parentheses. So a little different how it's going to be called, but the same functionality. And the default constructor just sets element to null, and this constructor right here, you pass in a pointer, and it will set element with that pointer passed in. So I think the iterator class overall is not so bad. So now I'm going to go over more details as to how we can sort of visualize our hash map structure with this iterator nonsense, so we can get a good idea of how we can sort of work the code out for this hash map class. Okay, so let's focus on this bracket operator, but really it's not going to, so it's going to be called the same way as you were call this for unordered maps. So this is sort of the snapshot of what we can see. Let me just zoom out so we can see all of this. This is sort of how the table, or is that going to be how the hash map class looks like. So basically we have at most two nodes in each linked list, and this is going to be our head, which is going to contain all of our actual elements in our hash map. And we have it so we can see here for this node's key and value are going to be two pointers that points to this node's key, and then this points to this node's value. And same thing for this node's key, this node's right here, this key field is going to be actual pointer to this node's key, and likewise this field here, it's going to be a pointer that points to the value field of that node. So these are the elements actually in our hash map, and this linked list right here below is going to store all of the actual elements we have, so we can cycle through them. But the whole idea of this is the following. So if I were to update the value field of a given node, then if I do a dereference of this pointer in this node, it's going to reference this value right there, so that way we have this nice shallow copy. So if we have three nodes, we're going to have three nodes over here as well, and we have shallow copies essentially. So this could have been done maybe a little differently, but I guess this was sort of the I don't know, straightforward way I was able to think of to approach this problem. So that's how we can kind of visualize this. So let's say, for example, we're in main, and I have, let's say, I have a hash map, and we're going to use strings, obviously, for the key types for this assignment. And I'll just maybe use int for right now, and I'll call this maybe just R. I don't know, just pick the letter R. So of course, just like we can use a bracket operator and just pass in hello equals, let's say, 7. So the idea when we have to actually do this lookup is the following. So you have to first locate where it's going to actually have to be stored in our hash table. So there's really a few possible scenarios. So if, let's say, just for the sake of argument, that hello would have to, let's say I pass in this hello. So of course the first thing we do, as always, is we take the actual string. So hello is going to be actually this T1 key right there. So we're going to take this key variable and pass it into a hash function. Let's say for hello, just for right now, let's say that index 0 is where hello has to go. Well, in that case, table index 0 contains a null, so we know for sure this would be a new element to be created. So of course we allocate the node, we assign hello to be this, and of course to assign a default value over here, we use actually t2 like this. So if I allocate a node, let's say I have a node I equals new hash pair. I say I arrow key equals key, and key of course is that parameter that we have right there. I could say I arrow value and equals t2 like that. That's going to assign a default value for the value field of this node. Then of course, since it's a new node to be created, we would have to of course allocate a new node over here as well. And of course, what we're going to do for this node, so of course, maybe I'll just for now, so I would be a pointer of type hash pair. I'm going to create j will be equal to new, I think it's called iterator pair. And of course, you would set j key equals to ampersand I key, because this is going to be sort of I key is a field. We're going to retrieve, maybe I'll zoom out so we can see this a bit better. This is going to retrieve the address of I key. And we're going to take the address of I key and assign it into j keys field. So j key is a pointer. It's going to essentially point to that key field. And of course, for the value, I could just say j value equals ampersand I value, because we're going to get the address. Remember, the address operator is in play here. I'm going to take the address of this element right here, and we're going to assign that address right over here, like so. So that's basically how we can actually set this up. And of course, you have to work out the actual kinks to actually insert it into that linked list, but that's sort of the idea of how you want to handle this. So we're creating a shallow copy of this object. So we're taking the address of this node's key, assigning it into this pointer, and the address of its value, assigning it here. So that means if I update this value at any point, then if I try to retrieve the value field, it's going to be updated. So it's a shallow copy basically. So now I won't go over all the details sort of for if we insert other scenarios, but this is basically, this is one case where if we have an empty sort of linked list, well, what happens there? Now let's go over a scenario where, well, we have other cases as well that could happen. So that was our first case, where if we actually have, if we're inserting a node into a blank linked list. Let's go ahead and sort of now go over another scenario here. So I'll erase all of this, but now you have this code obviously because it's it's on the video. You can pause the video at any time and write that code down. So now let's go over a scenario. So obviously, another scenario could be that this key hello already exists in our hash table. Well, in that case, as always, we jump to the index and we have to search that linked list until we find the matching key. If we do, return the value field of that node. So let's say, for example, hello happens to be in this linked list or this node right here. Let's say this is where hello happens to be. Of course, we call a hash function. Let's say a hash function in this scenario returns the value 2. So index 2 in this linked list right here is where hello has to be. So the first thing we'll do, we create a pointer, and a pointer is going to be set like this. So I would be set as table index. Of course, you would use that hash function. So I'll create a variable here, call it int x equals age of key, where key would be hello in this case. and I go table X, which will assign I. So I would be a pointer of type hash pair. And I would point to that node, and we check. So remember, we can just do I arrow key equals to key. If it matches, then simply return I arrow value. Return the value field of that node with the matching key. If it's not correct, well then we just do our normal I equals I arrow link approach to move I over to the next node, obviously. So that could happen as well. Now, let's say, for example, in this linked list, let's say after we check the first node and the second node, and they both don't have a match, that means hello can't be here, because remember, we kind of capped it where we will not have more than 2 nodes per linked list. Well, in that case, we're going to just set, x will equal to x plus 1 mod by size, and then try the same thing, but now I will be set to a new x. So now I will be set to the next elements. Index 3 is set to a null, obviously. So I will be set to a null. So, we just do this approach. We just set x to the next element over, and then the same thing. We're going to set I equal table index x. But of course, we're not going to call a hash function again. We're just going to basically just increment x by 1, and then using this new x value, we're going to, of course, say table at index x, set I equal to that, and of course, there's 2 scenarios. Either at some point I becomes null. If that's the case, that means we know we have a vacant spot in our table. So, for example, I guess here we would just insert. Let's say, for example, we have another scenario where, let's suppose that x happens to be 4. So obviously if x was 2 and we look at the first node and second node and there's no match, we're going to set x equal to 3, and then we're going to set I equal to table index x or 3. I will be set to a null, and we'll just insert the node right there, obviously. Now, let's say, for example, just for the heck of it, index 3 had 2 nodes also, and these 2 were also not matching hello, right? In that case, index 4 is where we're going to look. Let's suppose the first node does not contain hello, and then this node's link equals null. That means this entry only has 1 node inserted, so there actually is room for 1 more node to be inserted. In that case, you're going to allocate the node at the end, set the link equal to that new node. And then, of course, what you would do is create a new node in this linked list, and then set, of course, the pointers equal to, so set this node's address equal to that node's key, and set that node's value address equal to this new node's value. So just like from before. So now in that case, we have to also make sure we always are considering the load factor as well. So in this case, if let's say we have 1 node and we're going to insert a second node, then this entry now has become full. There's 2 nodes. So then increment items counter by 1, which means that this entry is now full in this table. So if it's empty linked list, you insert a new node, you don't increment items counter by 1. If it has 1 node and you're going to insert a new node, a second node there, then you have to increment items counter by 1, because now this entry would become full. So, of course, I guess I sort of made a mistake. I didn't make a mistake, but one thing you want to check for is before you even try to do anything in your hash table, the first thing you check is your load factor. If it's too high, you resize first, and then you go ahead and do all of this stuff that I was saying right there. But it doesn't really make the actual operator bracket function logic any more difficult. But that's the idea. So a new node gets created, you have to create a new node over here and set this node's key address and value address to point to that new node's key and value pair. So if I modify the value here, it modifies it back actually I might have thought a value here, sorry, then this is going to now point to a new value, so a shallow copy is established. So hopefully this sort of gave you a little bit of an idea. So now I'm going to go over the resizing function for hash maps, or for this custom hash map class. Alright, resize. So this function would be called in the bracket operator right before you do anything. The first thing you do is you check your load factor. So of course you take items divided by size. If that number is bigger than 0.5 or equal to it, you want to resize. Now, be careful with that calculation. Remember, items and size are both integers, so you have to do a typecast and then divide. So, because for example, if you have, let's say if our size or if our amounts is 2 divided by 5, this will give us the actual value 0, not 0.4, I believe is the correct decimal value. So you want to make sure you have to do a static cast, at least on that 2, to get 2.0 and then divide it by 5. So you have to static cast either the items or the size, or both. It's up to you, because otherwise you won't get the correct answers. This is a very common issue that happens with the resizing function, or in the operator bracket function that will check to see if a resize has to be done at all. Okay, so the resize function is going to double the table size. So you have to allocate a table of let's say in this case of size 10. You have to rehash everything in this table to this bigger table. Okay, so one trick to do this is, one kind of obvious way is you can copy and paste all the code from the bracket operator function, but that approach is kind of that's gonna make a code very big, and code gets very big, conglomerated like that, it becomes very hard to actually fix anything. So I recommend calling the bracket operator function within this function call. So I guess in a sense it's going to kind of give away the answer, which is kind of a shame in a way. But I won't give away everything. I'll give away a big chunk of it. So right now what I'm going to do is, what you could do is you can create a pointer let's see, I'm gonna call this, I think it's called hash pair. I call this old table, or you can call it obsolete table if you want. You want to set it equal to table. So when you do this, old table is going to point to this. And of course, you're going to set table equal to new hash pair. And I'm going to write this here in red with the updated size. So of course you have to update the size field, but I'm going to just for now leave this sort of, for you to figure out, updated size. Okay, so when I do this, it's going to allocate a bigger table. So I'm going to try to write this quickly. Okay, I think that should be good. All right, yep, perfect. So I'm going to go ahead. I'll just put the numbers. I won't put the brackets next to this just for the sake of time. It does take a long time actually to put brackets next to all of these. So table is not going to point to this. And what you can do is the following. What you can actually do now is you could say star this, and let's say for right now I create an I pointer. Maybe I'll use green to do this. So I would point over here to this node. So you could say I arrow key equals to I arrow value. So what this does is going to take this element, so I'll use green here to draw this, it's going to take this and it's going to hash this into this table. Remember, because the this object, it's going to call the bracket operator, and table is an instance variable of the this object, or of this HashMap class. So if I say star this bracket, it's going to map this into this table, because this table, or sorry, star this is an object, is a self-reference, remember, and table is going to be our instance variable. So the star this bracket operator is going to map the following, the green encircled node into the correct position of the this arrow table, if that makes any sense. And you have to do the following code for every node in the old table. So my mistake, this actually should be old tables, what I should have kept here. My mistake. I'm sorry about that mess up right there. So you want to copy the old, so old table remains there, of course, and table is going to be set to a new larger table. My mistake. And of course you want to go through all the elements in your old table, go through all the nodes one by one, and then call the bracket operator, so it's going to just magically map this into the correct location of the table right there. Now, of course, what's going to happen is if you do this, it's going to, you have to make sure that you have to deallocate this list first, actually. So I'm going to kind of leave this open for right now, but you have to deallocate the linked list right here, that the key value pair linked list, because you want to make sure these point, or it's up to you, but I would just say you first deallocate this, all of that, and then start mapping things one by one, and it's going to recreate this iterator linked list, or this list of all the possible hash pairs or iterator pairs, but which, you know, they point to their shell copies of the key and values of the linked list right there. You want to, of course, deallocate these, and of course, if I say star this bracket, it's going to allocate a node, and it's going to create a new element. It's going to create new elements in your iterator pair, or in the head linked list, if you will, one by one. Because the bracket operator, as we discussed earlier, is going to allocate nodes one by one, these nodes for this head linked list. But you have to first destroy this so it can recreate these as it's inserting elements from your old table into your new table. And then when you're done, you have to deallocate your old table to avoid any memory leaks, because now the following table right here, that's going to be a new resized hash table. So the old table is now obsolete. We're going to go ahead and deallocate that. So hopefully this resizing function, or this explanation here, was helpful for the resizing function. So that kind of goes over the HashMap class. So now I'm going to go over the contents in main and the input files and so forth. Okay, so once again, in the contents of main, you may have to allocate a few HashMap objects. It's up to you how you want to set this up, but for the key type, I'd recommend using a string, because obviously you're going to be doing a lot of string lookups, and you're going to map it to a to a different type, possibly a string or integer and so forth. So you have to use a hash map to do all your lookups. No linear searches can be done. Of course, you maybe can sort of think about the brute force way, which would involve doing some linear searches, and then try to think of a way to enhance it using a hash map. Now, of course, what you can do is, since this program has a lot of moving parts, as in you have to create your HashMap class. You have to also use that in main, and there's a chance that, well, you could have a seg fault, or who knows what in the heck could possibly happen when running your program. So one thing you could do is you can use unordered map just to see if your main algorithm that you wrote at least works, because unordered map is going to work. It's a type that definitely works. So that way, when you run your program, the scary part that could happen is it won't work, and then where do you even begin to figure out what's wrong with your program? I mean, is it your hash map that's messed up? Is it your main algorithm that's messed up? So using an unordered map first will give you, at least you can get an idea of how this program, to make sure if your main algorithm is actually correct. And if it is correct, it's working, it's matching the output, then of course now try to include your hash map. So everything about hash map and unordered map will be exactly the same, except for the iterating through all your keys. It's not going to be arrow first, it'll be dot first, left and right, paren, and dot second, left and right, paren. Other than that, the begin and end should work the same. And then of course iterator plus plus moves to the next node, next element in your hash map, and so forth. So that's kind of the hints as to how to begin main. Now of course I'm going to now go over the input output, which will be kind of where I'm going to sort of describe sort of how you want to write your algorithm for your main program. Alright, so for the input, well, I guess you can sort of read through this, but I'm going to actually just show you a test input file and then of course explain it, and of course you can read through this as I explain it. So here's our first input file. I'm sorry for that bright light that just might have flashed right in front of you right there. Let me zoom in. So the first this file will have the following setup. This problem was actually chosen from one of the competitive coding problems. So this input is actually, I just copied it from that competitive programming problem sample input output. The other input output files I provided are kind of more custom. Let's go over this first one. So the number at the very top, this first number, will tell you how many test cases you're going to have. Okay, so in this case we have one test case, so I guess one election, I suppose, here. And then this 3 tells you how many candidates you're going to have. You have 3 candidates. Okay, so then you're going to have 3 pairs of lines. So actually you're going to have 6 lines here, because every candidate has a name on one line by itself, followed by a party name. I don't know why is it Rhinoceros, and I don't know why we have Marilyn Manson here. But okay, Marilyn Manson is running in the party called Rhinoceros. That's okay, let's go with that. So anyway, we have 3, which means there's going to be 3 candidates in this particular race. So we first have first candidate Marilyn Manson in this party. Then we have Jane Doe in this party. And then we have John Smith in independent. Okay, so the way it's going to be set up is that there will be no more. So for example, Rhinoceros, there will be no more than one candidate representing this party. So Rhinoceros only has one candidate, Family Coalition has one candidate, but independent, however, independent is not really a party affiliation. So there could be more than one candidate who is independent, but there cannot be more than one candidate that's in the party Rhinoceros or Family Coalition. So if you have, so I guess just to summarize this, we have 3 candidates, which means we're going to have 3 pairs of lines, or 3 pair of 2 lines, I should say. So 6 in total, because we have 1 line for the candidate name, and then 1 line for its party. Okay, so that's our first part of the input. Now, our next input portion will have the number 6. In this case, 6 meaning there's going to be 6 total ballots that were cast, I guess. So then we have 6 lines. 1, 2, 3, 4, 5, 6. So John Smith gets a vote, Marilyn Manson gets 1 vote, another one for Marilyn Manson, Jane Doe, John Smith, and Marilyn Manson. So we can see here Marilyn Manson received 3 votes. So Marilyn Manson won the election. So I guess I'm going to go and switch to the output portion. So the output basically is going to just output the party name of the person that won. So since Marilyn Manson got the most votes, then you can output test case, and you can output the party that Marilyn Manson is involved with. So you can output rhinoceros. And that's what we have over here. So that's the output kind of. So that's really all you have to do. Output the party. Now, of course, if there's a tie, so you have more than one candidate with the same number of votes, just output tie. That's basically the idea. So that's really the output. Let's look at more input files just to kind of just look at the rest, summarize the rest of these input files up as well. This also has only one test case. We have 4 candidates here. John Smith, independent, and then these are names I kind of generated randomly. I guess Democrat, Republican, and this person independent. We have a lot of votes this time for each candidate, and of course you output an amount. And then input 3. We have 1 candidate. We have, or sorry, 1 test case, 11 candidates, and these parties actually do exist in the United States. So I went to Wikipedia and looked up these parties. These are actually parties we have here. So I used that, and I didn't include every possible party name because some of those one party in particular that I just don't want to include in this sample input file. If you were to Google the party names and you see it, you'll know exactly which one I'm talking about. So I cannot include that one in this file for obvious reasons. So that's that. So here's another example: 1 input, 1 test case. Here are 11 candidates. You have this many possible ballots that were cast, and of course we have Ralph Nader there, which was, I remember way back, I think back in 2000. Ralph Nader was the Green Party candidate. So yeah, so here we have a lot of ballots that were cast. You have to count them all up and then compute the winner and output the party they're associated with. That was input 3. I think input 4 is the same thing, just a little bit different. Just different. I think different ballots. Same. I think it's the same actual candidates, but different ballots. Then input 5, the last one. This one will have more than 1 test case. So I guess this is for the case where a recount was done, I suppose. So if you actually remember the 2000 election with Al Gore and George Bush, then there was several recounts in the state of Florida because it was a very close race in Florida. So I guess this is going to be a recount. So we have 3 test cases. Each test case is the same. I copy the same candidates but different ballots, I guess, in each one. So our first test case, we have these candidates. These are all of our ballots, and of course once all the ballots are done, see if I can actually get through all of this. So then, okay, then there we go. And now this ends. This is the last ballot cast for this first test case. So now we have 5. This is going to be for our second test case. You have 5 candidates, the same people, different order this time, but then we have to, of course, we have a different amount of ballots. So we go through all these ballots, we have to count these all up, and then let's see here. Oh, I think I might have skipped over. I might have gone too far. There's supposed to be a third ballot here somewhere. This might have just went by too fast. Anyway, it's not important. So there's actually 3 test cases here. So here is the output. So for first one, rhinoceros. Input 2 was a tie. Input 3 is Green Party. Input 4, Alliance Party. Input 5, we had 3 cases. And every time it was different. So this was interesting. It's going to be a very controversial result here, I guess. So that's that. So of course, make sure your program is memory leak free as well, and only use no searching allowed other than using a HashMap object. So I'll go over right now. I'm going to show code grade as to see how you can sort of verify if your program does or does not have memory leaks. So I'm going to go over that last part next, and then we'll be done with this assignment video. Alright, so again, as always, we compile our code and everything. So pretty much use the same inputs like that's showing in the input, in the PDF, sorry. Using the same inputs as in the PDF, just this is more automated testing, so it's easier on the graders. So of course, we want to check everything. Of course, we go to output, and then we can check errors, and that's where it shows the memory leak summary. So in this case, all heap blocks were free. That's the answer you want to actually see. So this is for my code. So again, yep, no memory leaks. This is how you can check to make sure there's no leaks possible. Awesome. So that's all good news right there. So that's how you would check for that. And of course, when you actually, you know, as always for code grade, if they didn't match the output, then you can actually check the output, and there's actually a diff option here somewhere which can tell you what was the issue. So make sure everything is sort of in the same upper lower cases like that, just to make sure that everything works. Now, of course, as always for the code grade, I sort of have it skip all white spaces, so that way so I won't be very picky about that, because that sometimes code grade does give issues where there's some really random, bizarre, hidden characters somewhere, and code grade is going to mark that wrong in that case, so you don't want that. So of course I have code grade skipping over that. Other than that, that sort of concludes the video. I hope this video did help you, give you an idea of how to approach the problem. So I guess for now, happy coding, and until next time.